Hello everyone, welcome to my presentation. My name is Jiaming Ma, one of the 4 recipients of the 20th Hangai Prize. I'm a postdoc researcher from the Center for Innovative Structures and Materials of RMIT University, Melbourne, Australia. In today's presentation, I will show you the design and construction of our new rib floor system achieved using the latest digital technologies. The title of my presentation is PrintNervi, Design and Construction of a Rib Floor System in the Digital Era. Let me start by giving you an interesting fact. According to the literature, it is reported that 40% of carbon emissions around us are produced by buildings we all live and work every day. Did you know the floor systems, including the slabs and columns, can occupy up to 85% of the total weight of a building? Inspired by this, if we can improve the material efficiency and reduce construction costs in the floor system, perhaps we can significantly reduce carbon emissions, thereby minimizing the environmental impact. As shown in this picture, traditional floor systems are typically made up of slab ribs in an orthogonal layout. However, researchers have found the structural efficiency of such a layout can be greatly improved. Besides, the traditional construction method can produce a significant amount of material waste. We also want to highlight that the standard layout can be changed, such as introducing curved features, so that the aesthetics quality of the floor system can be improved, thereby achieving elegant designs. In the last century, Pierluigi Nervi, one of the most famous engineers, had produced many iconic roof floor systems using the concept of freeform geometries. These include the Gatti wool factory and the Palace of Labor in Italy. Without digital computational tools back in the days, Nervi had to design his slab ribs manually using the isostatic lines of principal bending moments under uniform distributed loads. Also, fabrications of his slabs and columns were extremely labor-intensive and limited to conventional construction materials. To this end, we believe that using the latest digital technologies and new materials can lead to an improved version of Nervi's system. Our starting point was actually inspired by Nervi's slab and column designs, as highlighted on the screen. Here, we utilize new digital technologies to create an improved version of Nervi's system. We call it PrintNervi. In detail, we use the topology optimization method to redesign the geometry that has an enhanced structural performance. We also use digital fabrication methods, including 3D printing and CNC machining, to automatically manufacture parts required during the construction. Together, we can achieve a new floor system that is more structurally efficient and more sustainable and less expensive in terms of the construction. We use the BESO method to optimize the rib layout. The basic idea of this method is to gradually remove materials from inefficient regions and add materials to where they are needed, iteratively until prescribed volume is satisfied. The objective function is compliance minimization, equivalent to stiffness maximization, as shown in the first equation. In each iteration, we ensure the static equilibrium using the second equation. Ultimately, a prescribed volume is reached, controlled by the third equation. During optimization, we assign each building block to be a really small number close to 0 or 1, corresponding to void and solid elements, represented by the last equation. In this research, we propose a modified topology optimization method which includes 2 new techniques. They are constraint mapping and structural complexity control. We set the optimization problem using a multi-layer slab. Using conventional topology optimization methods, we may end up with an ununiform thickness result. Here, to ensure the optimized ribs have a uniform thickness so that they can be easily and inexpensively manufactured later, we set all the blue elements in the same column to be either all solids or all voids during optimization. We also use a structural complexity control method to guarantee the rib continuity. Using our method, we ensure the early topology to be maintained in the final result through changing the shapes of the voids without merging them, so the bars between the voids can be preserved. Here is the demonstration of our new optimization method. On the left is the optimization problem. Due to symmetry, we only simulate a quarter of the floor unit, which is a simple square, and the target volume of the ribs is set as 28% of the square, as the original design by Nervi. On the right is the video showing the optimization process. Based on the optimization result, we can generate a rib shape by tracing the boundaries. We want to highlight that this elegant shape is completely designed by the computer, which is naturally determined by the structural system and without human interactions. Together with the original column from Nervi, here we show the final 3D model of the new floor unit. On the left is Nervi's original design, and on the right is our PrintNervi. In comparison, it can be seen that our design do not have ribs with a uniform width. The optimizer distributes the materials to where they are really needed. Hence, more materials are allocated near the support region. We use the compliance to evaluate the stiffness performance, which is the inverse measure of stiffness. It can be seen that our PrintNervi is stiffer than Nervi's original design, as our design has lower compliance value. Specifically, our design is approximately 26.3% stiffer than Nervi's original design. The image on the left shows the formworks of our PrintNervi, which were manufactured using two most common digital fabrication tools, including 3D printer and CNC machine. The white parts were 3D printed and the blue parts were CNC cut. The whole column formwork was 3D printed by a KUKA robot with a PETG pallet extruder. An zigzag shape infill was implemented for the formwork shell to enhance strength for casting. To provide extra tensile strength for the concrete, 4 vertical reinforcement bars are prefabricated and installed inside the column formworks. The column formworks were assembled using bolts horizontally and turnbuckles vertically. The flat panels of the slab formwork were CNC cut from plywood as a balance between strength, cost, and sustainability. The two-layer reinforcement was also prefabricated according to the shape of the ribs and installed within the slab formwork. The fabrication of the whole formwork, including the slab and column, took less than 90 hours in total. After the formworks and reinforcement were settled, industrial grease was applied to the formworks, which can protect them from demolding. Then the concrete was poured, vibrated, and leveled, as shown in the photos. After 2 weeks, the concrete has gained sufficient strength. The formworks can then be easily demolded. In this photo, the slab was lifted and mounted temporarily on a 1-meter column to facilitate the demolding process from the bottom. You can see my colleague on the left was demolding the 3D printed formworks using very simple tools. Here is the demolding result. Later, once all formworks were removed, the slab was lifted to the full-size column to complete the assembly process. The image on the left shows the intricate surface of the cast column, which had a really nice surface texture. The image in the middle shows the final assembled floor unit, which was around 2.5 meters tall. The right image shows the used formworks. It can be seen that they are still in good conditions and ready for casting new slabs and columns. In addition, both plywood and PETG materials can be recycled if the formwork is not used anymore. We believe that our proposed construction method is not only inexpensive, efficient, but also sustainable. Overall, The proposed design and construction methods from this project offers a contemporary evolution of Nervi's pioneering techniques for creating roof floor systems. The major conclusions are: first, a modified topology optimization method is developed for enhancing the structural stiffness of roof floors. Second, using the new method, the optimized roof slab can achieve higher stiffness than Nervi's original slab design. Third, the hybrid digital fabricated formwork can cast free-form geometries with minimal material usage, adequate rigidity, and intricate shapes. Fourth, the formworks from PETG and plywood materials are reusable and recyclable. Last, despite a shortage of computational tools for engineering analysis in the last century, Nervi's design and construction concepts were groundbreaking and are still considered pioneering even by today's standards. This brings me to the end of my presentation. Thank you all for listening. I welcome any questions or comments from you. You may contact me through my email or scan the QR code on the screen. And finally, I would like to show you a short video to review this project.